Chapter 2. We are going to define voltage, current, and resistance. In order to define voltage, current, and resistance, we have to study the atom model. And the model we are going to be using is the Bohr atom model. And in this one, we have the nucleus that is composed from positive protons and neutrons, and then we have the electrons moving around it. Why is this important? Because we want to study how electrons move from different valence shell, so we can determine if the material it is a conductor, an insulator, or a semiconductor. And by defining how many electrons we have on the outer valence shell, we can decide in which category this material or this element falls into it. So they give us this example right here, silicon. It says that it has 4 electrons in its valence shell. So if we look at the periodic table, we see that it can hold more electrons here. So therefore, silicon it is in semiconductor, as we saw that most of the chips are made from silicon. More about how the behavior of the atom, we can study that for chemistry, I guess. We're going to continue, and once we have that, we study the electron motion. So well, that's what defines actual voltage. So voltage is how much work it will take the electron or the charge to be moved against the electric field. So in the next slides, we are going to actually formally define what a voltage is. So voltage is the potential difference between 2 points. So right here in the previous picture, we have a potential difference between this point and that point. So what it says is that the work it takes us to move 1 electron from the negative to the positive, which is against the electric field, is going to define voltage. So the units are going to be volts, work is units are joules, and then the charge that we are moving, it's a coulomb. So the definition of voltage, it is work over charge or joules over coulomb. Right here we have different voltage sources, how we can create power or voltage for our, so that we can do some work. So we have solar cells, fuel cells, batteries, and different examples of power sources. So what is an ideal voltage source? Unfortunately, we are going to only deal with ideal voltage sources because we don't have the lab open. So the simulation, it takes care of the ideal voltage source, where we have the I that stands for current and V that stands for voltage, and says that in an ideal situation, the voltage source, it is the same voltage all across, independent from the current. So the current can go to infinity and we are still going to have the same amount of voltage. In practice, this is not the case. We have some variation, but definitions or new models nowadays are pretty close to being ideals. Now we are going to discuss current. Current is the amount of charge that flows past a point in a unit of time. So current, we can say, is like a rate. So we have this section right here, and then we have a little opening or a little mark here, and we say we count how many charges go through here, so in a specific time, and that is going to be our current. So the units of current are amperes, and they are defined as coulomb over second. So time is in seconds and the charge is in coulomb. Right here, coulomb, unit of charge. And this is important because sometimes they tell us how many electrons we have in a specific area that is traveling, in a specific cross-section area, and we can still get the current. So we are going to do examples in this chapter later so that you can see how this is applied. So here is a little formula that I gave you, that what is the electron charge is 1.6 times 10 to the negative 19 coulomb. So if we have a specific number of electrons, we can find how much current we have, and we use this formula that 1 electron divided by the electron charge will give us the amount of charge, so that we can get the current. So right here they're asking us a practice question. The nice part of these equations is that it is a single equation, so we have to have two unknowns to find the third unknown. So right here it says I have a current. What is the current if I have two columns and they are passing a point in 5 seconds? So we just plug in here 2 divided by 5 and we get 0.4 amperes. Next, the same idea as with voltage, we have the IV curve, the current and voltage curve, and in this case it doesn't matter how much we increase the voltage, the current stays constant. And this is the ideal current source. In reality, we have a small variation. This is how a current and a voltage source will look like in reality, and in practice we deal with voltage sources just because they are easier to maintain, easier to make. So most of the labs will carry voltage sources, and from voltage sources toward the end of this class you'll see how you can make a current source, which is more stable but more expensive to make. Resistance. Resistance is what resists the motion of electrons. It resists current. The motion of electrons is current, so resistance resists that. So how do we see it? In practice, we say that anything that we make do something, it is a resistance. Something that the energy or the voltage is used, it is a resistance. The units are ohm. If the current is in amperes and the voltage it is in, and the voltage is in volts. Sometimes we are interested in finding the conductance. The conductance, it is equivalent to the inverse of the resistance. So what is a conductance? It's how good something resists current. That is the measurement that we are very interested in. How good something it is designed to resist the flow of current. Most of the resistors that we would use in the lab would be ceramic resistors like these ones, and they have colors that are assigned for us to find out or to figure out their value. So they don't have numbers printed, but also they're being standardized in a way that we can read the colors with a table and find out what is the value of that resistor. So here is a table. So the resistors we are going to be using is a 4-band resistor. There are different bands, 5 and above, but we are going to concentrate on the 4-band because those are the easier, and then we can expand onto that in later classes. But in this class we are going to concentrate on the 4-band color resistor. So here are how they are associated. We have black, brown, red, orange, yellow, all the way to white, and they have associated from 0 to 9. Okay, so the way we read a resistor is the first value. Let's go back to the previous one. You see it has 4 values here. we start reading them from here. So this will be the first band, this will be the second band, this will be the third band, and this will be the fourth band. So the way we read it is that the first band is the first digit from 0 to 9. The second band is the second digit from 0 to 9. The third band, it is the multiplier, how many zeros we can add. And the fourth band, it is the tolerance. Okay, so how does that make sense right here? So if I'm in the first and in the second digit, I'm just going to read the color and go straight. Okay, if it is red, then I just take the 2. If it is yellow, I just take the 4. If I'm in the third band and I'm in green, I will not use the 5. I will use 5 to the power of 10 to the power of 5 because it's my multiplier. And then the fourth band, it can only be gold or silver. Gold stays for 5% tolerance and silver stays for 10% tolerance. We're going to stop here and continue in the next video.